very good morning and welcome to this course on the foundations of continuum mechanics. Today we'll be going through the tutorial for week 8. So let us get started. So we will be covering 5 problems from the following topics, which include the displacement field, deformation gradient tensor, finite strain tensors, the Lagrangian and the Eulerian one, and the infinitesimal strain tensor epsilon. So let us get started with the first problem. So in the first problem, the motion of a medium is given by these equations, which is basically the chi function. And we have to determine the displacement field in both the material, that is Lagrangian, and the spatial, that is Eulerian descriptions. So let us solve the problem. So we know that the displacement u is given as small x minus capital X. So first we'll express this displacement in the material coordinates. So small x is written in terms of capital X, that is the chi function, minus capital X. So with this, we get u1 as a function of capital X is small x1 as a function of capital X minus capital X1. And we can substitute this expression for small x1. This becomes capital X1 e to the power of t minus capital X3 e to the power of t minus 1 minus a capital X1. So we can combine these terms. So this becomes capital X1 minus capital X3 into e to the power t minus 1. So this is the expression for the first component of the displacement in the Lagrangian description. In a very similar fashion, I can express u2 in the Lagrangian coordinate system as x3 minus x2 into 1 minus e to the power of minus t. I'm not showing the work here, but you can try it out yourself and you'll see you'll get the same answer. And then u3 becomes a 0 because x3 is given to be capital X3. So let's call this A, which is the displacement field in the material description. Now, next we have to express this, that is, we need u as a function of small x's, but for that we need the transformation chi inverse so that we can go from the Lagrangian to the Eulerian description of u. So we'll go back to the equations, that is the chi function, and then we will try to invert it, which is again straightforward because x3 is capital X3, so that's easily inverted. And since capital X3 is small x3 and capital X3 is small x3 in these two equations, I can easily write capital X1 in terms of small x1 and small x3, and I can write capital X2 in terms of small x2 and small x3. So when we do that, we get the following chi inverse function, and this we will call the set of equations B. Now using A, which is the Lagrangian description of displacement field, and B, which is the chi inverse function, we can now express the displacement field in the Eulerian description by simply substituting for capital X1, capital X2, and capital X3 in the Lagrangian description of displacement field U. And this will give us U1 as small x1 minus small x3 times 1 minus e to the power of minus t, and the following expressions for U2 and U3. And this we call the set of equations C. So we have completed what was asked in the problem, that we have expressed the displacement field in both the material and the spatial descriptions. Now in this tutorial, I'm not showing each and every step in the interest of time, but I urge you that you follow all the steps and make sure you fill in the gaps by reaching the answer that I've shown in the tutorial. Now here's problem 2. This displacement field is given to us, where these coefficients are constants, that is, they're independent of the material coordinates. So what we have to show in the problem is, first, we have to show that this displacement field corresponds to a homogeneous deformation. That is, at different points in the body, the deformation is all the same. In the next case, we have to show that if the constants aij's are small, then we can regard this deformation as infinitesimal, with the idea that products of different components of A are much smaller than the individual components of A. And finally, and this is the most interesting part of the problem, where we have to show that if there are two sequential infinitesimal deformations, then the order in which they appear does not matter in this case. So let us solve the problem. So in part A, we have to show that this displacement corresponds to a homogeneous deformation. So first we have to go to the definition of homogeneous deformation. This is the deformation when the deformation gradient tensor Fia is independent of the coordinates capital X. So as I move around in the material body, all points deform in a similar fashion. Now in this case, the displacement field is given to us, so we can find a relationship between the F tensor and the displacement field. So U I is given as xi minus capital Xi. So I can differentiate this with respect to A to get xi comma A minus capital Xi comma A, which actually is delta Ia. So I get xi comma A as ui comma A plus a delta Ia. And this xi comma A is nothing but our deformation gradient tensor. So all I need to do is I need to find ui comma A from this displacement field, and that should give me the deformation gradient tensor, and then I can check for the components of f not depending on capital X's. So when I take the first derivative of u1 from here, if I write u1 for example, that becomes a11 x1 plus a12 x2 plus a13 x3. So from here we can see that del u1 by del capital X1 is an a11. Similarly, del u1 by del capital X2 is a12. So we can see that this displacement gradient tensor is simply the matrix A. And since F is u plus delta, we simply add 1 to the diagonal components of ui comma A, and we get the deformation gradient tensor. And since A's do not depend on the capital X's, then this means that Fia is independent of X's, which means that this is a homogeneous deformation. So that completes part A. So for part B, we have to use or check for the infinitesimal deformation in this case. Now remember, infinitesimal deformation theory was valid when the ui comma A components are small. And this is when we neglected the product of the components of the displacement gradient tensor with respect to the individual components. That is what gave rise to the infinitesimal strain tensor. So from this logic, infinitesimal deformation theory is valid when the components of the matrix A are small, so that we can neglect the product of components of A with respect to the individual components of A. So if the components of Aij are small, this means we have a small deformation That means we are in the regime of the infinitesimal deformation theory. So we can define a strain tensor. So coming to part C now, in part C, we have to work with two sequential infinitesimal deformations. So let us do that. Now since U is defined as the matrix A times capital X, so we'll call the first deformation as the matrix A1 because each deformation is different, so it will correspond to a different A matrix. Let's say this is 1 and U2 could correspond to A2 times X. But what is given is that the deformations are happening sequentially. So it's best we work with the small x's here. So a capital X, that is the material coordinates. Let us say the deformation, which is designated by A1, it results in small x's. Let's call them small x1. So small x's are the new positions of the material particles because of the deformation. And now another deformation happens, which is A2, and this results in a newer position of the particles, which is designated by x2. So you see that we go from the material configuration to x1 to x2. And x2s are the final positions of the particles due to these two sequential deformations. So it is best we work with small x's, not the displacements in this case. And since u is defined as small x minus capital X, so this implies small x is u plus a capital X. And since u is given as a times capital X, so small x becomes a times capital X plus capital X, which implies that small x is equal to an a plus identity times capital X. So let's apply this into practice. So let's go for the first step, that is this one. So this results in x1, which is a1 plus identity times a capital X. It's better we write in the initial notation now. So I can say small x1 with an index I is aij1 plus delta ij times capital X j. So this we'll call 1. And now we apply the second deformation. So this is x2i is aij2 plus delta ij times, now this started from x1, small x1, so we have a small x1j here, and this we'll call 2. So now the aim is to express small x2 in terms of the starting capital X's. So from 2 we see that small xi2 is aij2 plus delta ij times small x1j. So I use equation 1 here. So this becomes ajk1 plus delta jk times capital X k. For clarity, I'll change the indices in equation 1. That will be much easier to see. So now it is much easier because we have an xj1 and xj1 here, and I use an index k, which anyways is repeated, so that's allowed. So this does not interfere with my index I in the second equation. Right, so let's expand the right hand side. So this becomes aij2 times ajk1 plus, now we have a multiplication with deltas, so I'll apply the substitution property as well. So this becomes aik2 plus aik1 plus a delta ik
times an xk. Now these are small, well, smaller than these, so I can neglect this in comparison to the other coefficients of a. So this approximately becomes aik1 plus aik2 plus a delta ij times xk. In fact, let's call it xk, and then plus a delta ikxk, which becomes xi. Because ultimately you have to write the displacement. So the displacement ui, which is from, let's call it 2, because that's the final one. This is equal to aik1 plus aik2 times xk. Let's box this. So what do we see here? That the final displacement is simply the sum of the two matrices which describe the two deformations times xk. So it doesn't matter in which order I perform the deformations, because it's a sum of the two matrices and the sum is commutative. So which means that the deformations can happen in any order and we'll still find the final same displacement. So this completes the second problem. Let us have a look at the third problem now. So let us understand the problem. We have this given deformation field where alpha is a constant, and we have to determine the matrix forms of the Lagrangian finite strain tensor and the Eulerian finite strain tensor. So this is a finite deformation we're talking about here. And then we have to show that the particles which lie on this circle in the material configuration, they deform also into a circle which has a different radius in the Eulerian configuration. So this is an interesting exercise because it tells us the locus of all the points from a given material configuration to a given Eulerian configuration, and it helps us visualize how the deformation affects the body. So let us solve the problem. So first we'll write the deformation gradient tensor f, which is defined as xi comma a. Now we have to find the Lagrangian finite strain tensor, which was defined as C minus I, where C was F transpose F. So twice of E is F transpose F minus I. So I can write my E as half of these. So since F is known now, I can substitute that here and I can evaluate the Lagrangian finite strain tensor, which will come out to be half times alpha squared 0 0 0 alpha squared 0 and all three zeros here. So this is our Lagrangian finite strain tensor. As a quick check, although that's not asked as an exercise in the problem, but we can check that d small x squared minus d capital X squared upon d capital X squared, this was given as n hat dotted with a twice e dotted with an n hat. So if you check this for, let's say, n hat equal to I1, what you get is you get twice E11. And what is twice E11? So this is E11. So twice of that, there's a half here. So that is alpha squared, which is alpha squared. But to be able to check that, we need to have some understanding of the deformation. So let us do that now. And again, this is not asked in the problem, but I'm doing that to give you a feel of what the deformation looks like. So let us say we have a cube with points A, B, and C, and point P is where we are quantifying the strain tensors. Remember, this cube is a small cube. So the coordinates of point A is L comma 0, B is 0 comma L, and C is L comma L. So as the deformation happens, what we'll notice is that x1 of A is capital X1 of A plus alpha times capital X2 of A. Now since capital X1 of A was L, so this is an L, and small x2 of A is capital X2 of A minus alpha capital X1 of A. And since capital X2 of A is a 0, this becomes a minus alpha L. So for visualization, let us say that alpha is half. So this point A becomes A prime now after deformation, and the components of the coordinates of A prime in the spatial configuration is L comma minus alpha L. So it goes down, as we can see. So this element PA becomes PA prime. Similarly, for point B, you will see it goes to the right like this, which is B prime, and it has the coordinates alpha L comma L. So this becomes something like this. So let us look at the coordinates of point C. So small x C1 is x1c plus alpha capital X2c, which is an L plus alpha L, and small x2 of C is capital X2 of C minus alpha capital X1 of C, which is L minus alpha L. The point C is somewhere here, C prime here, L plus alpha L, comma L minus alpha L. So if I try to see the element, it looks something like this. So it looks as if the element has rotated, but we can't really say that unless we have a look at the strain tensor. So the strain tensor does have elements. So this means that this is not a pure rotation, because we saw that pure rotation happens when capital E is identically 0. But actually, if alpha is small, then alpha squared is much smaller, so we can neglect alpha squared terms. So for infinitesimal deformations, these alpha squareds can be neglected, so this becomes a 0, and for that infinitesimal deformation case, this actually denotes a rotation. But if alphas are not small, then this is not a pure rotation, right? But we have to check this quantity. So d capital X was an L here, and d small x is this length here, which, if you see the coordinates of P, which is 0 0, and coordinates of A prime, you can see that this L prime is given as L squared plus alpha L squared square root, which comes out to be L times 1 plus alpha squared square root. So this definitely is not a pure rotation, because the length has changed. There is some stretching as well. But again, we'll not worry about that for now. We will discuss about how to understand finite deformations in the coming week. So for finite deformations, all this interesting stuff that is happening is visible in the Green's deformation tensor C that we had discussed earlier. Right, so this is our small dx. So small dx squared minus capital Dx squared upon d capital X squared is L squared into 1 plus alpha squared minus L squared, because d capital X was an L, and this is L squared. So this becomes simply alpha squared. And this agrees with what we find in the Lagrangian finite strain tensor E11 component. I'll leave that to you to check the off-diagonal terms, that is E12 and E21, by looking at the angle between these quantities. So please check that if you take N1 and N2 along x1 and x2 directions, you should see that this gives you an E12 and this should give you a 0 because the angles, right angles, have not changed. Right, so now that you have some understanding of the deformation visually and geometrically as well, let's continue the problem. Now the next part was to find the Eulerian strain tensor small e. Now the Eulerian strain tensor is defined as half of identity minus F inverse transpose times F inverse. So we need F inverse now. Now one way is that we already have found F, so you can invert it. And the other way, which is much simpler, is that F inverse was defined as capital X A comma I. So if we can get the inverse transformation from small x to capital X, I can find F inverse easily. So we have to find chi inverse first. And to find chi inverse, we must check the Jacobian not equal to 0. So the Jacobian is, it's a determinant of f only because that was x I comma a. And if I look at my f tensor, and this is how my f looked. So if you try to find the determinant along this row, for example, this is simply 1 plus alpha squared. So the Jacobian is 1 plus alpha squared, which definitely is not equal to 0 because alpha squared is a positive quantity. So this implies that inverse possible. And now we find the inverse, which I'll leave it to you to find that because we have done enough problems to find inverse transformations. Right, so now that we have the capital X's in terms of small x's, we can find F inverse, which is capital X A comma I, which comes out to be this. And since we have an F inverse now, we can calculate the Eulerian strain tensor or the Eulerian finite strain tensor with it, which has this form. So this completes part B of the problem. Right, so we have found the tensors E and small e, and now we have to show what happens to these circle of particles in the material configuration after the deformation. So let's do that. So we have a circle of particles given as capital X1 squared plus capital X2 squared equal to 1. So in the material configuration, we're talking about a circle which has a radius of 1 and all the particles lying on this blue circle will deform into some shape in the deformed configuration, and that is what we have to find. So that's a straightforward problem because I have capital X's in terms of small x's. So I substitute the inverse transformation here. So we use chi inverse to get this equation. And now if I expand this, we get this equation. Now we can see that these terms cancel. And I can combine the x1 terms and x2 terms together, which gives us x1 squared times 1 plus alpha squared plus x2 squared times 1 plus alpha squared upon 1 plus alpha squared whole squared, that's equal to a 1. So this simplifies to x1 squared plus x2 squared equals a 1 plus alpha squared. And that is exactly what we had to show. This indeed is a circle with a radius of square root of 1 plus alpha squared. So in the deformed configuration, the circle remains a circle, but the radius increases. So this completes the solution. So here's problem 4. Let us understand the problem first. We have the deformation given by these equations or the chi function. First, we have to determine the Lagrangian finite strain tensor capital E, and then we will use the condition that if k is small, then we can get the infinitesimal strain tensor epsilon because under small deformations, capital E becomes epsilon. And thirdly, we have to verify this epsilon that we have gotten in part B with the definition of epsilon obtained from displacement gradients. So let us solve the problem. So to get capital E, first we need the deformation gradient tensor, which for this case becomes del small x1 by del capital X1, which is 1, then del small x1 by del capital X2, which is a twice k x2, and that this is a 0. Similarly, del small x2 by del capital X1 is a minus twice k capital X1, then a 1, 0, 0, 0, 1. And then the Lagrangian finite strain tensor is defined as half of F transpose F minus I. So when we substitute the expression for F, we get this form. So this completes part A. The part B requires us to use the condition that if k is small, then that will be the condition for infinitesimal deformations or small deformations, and capital E becomes epsilon. Right, so if k is small, then capital E becomes, now the first term here is a k squared, which is much smaller than k, so this can be neglected. So this is a 0. K times x2 minus x1 is retained because it only has one k, and similarly we have the other terms, and this indeed is our epsilon. So that completes part B. Now in the third part we have to find epsilon ij as the definition from displacement gradient tensor ui comma j, and we can see the displacement ui is small xi minus capital Xi, and this is equal to the vector k x2 squared minus k x1 squared and a 0. So from this I can easily find ui comma j and uj comma i's and add them and divide by 2 to get an epsilon, which is exactly what we had gotten in A. So since both are the same, this completes the solution. So now we get to the final problem for today's tutorial, and in this problem a strain rosette is given to us, particularly the delta rosette, which is in the shape of an equilateral triangle. So let's draw that. So these are the three strain gauges, and the angle here is 60 degree because it's an equilateral triangle in a delta rosette as discussed in the lecture. So as we discussed in the lecture, that strain gauges are used to get an estimate for the shear strain by measuring longitudinal strains in different directions on a surface. So when we paste this arrangement on the surface, we get the values for epsilon 11, epsilon 11 prime, which is along this direction using this strain gauge, and epsilon 11 double prime, which is in this direction using this strain gauge. So using these three longitudinal strains measured by the strain gauges, we have to find the values for epsilon 22, which is a longitudinal strain in this direction, gamma 12, which is engineering strain in the 1-2 plane, and epsilon 22 prime, which is at 90 degrees to x1 prime here, so that is this direction. So let us solve the problem. If I write my epsilon in the coordinate system px1, x2, x3, my epsilon can be written as like this. Now if I try to write epsilon prime, which is the strain tensor when seen from a coordinate axis which is rotated by 60 degrees counterclockwise around the x3 direction, which basically will give us this as the x1 direction. So this epsilon prime becomes like this. So this is epsilon prime in the rotated coordinate system. Now there's a relationship between these two using the tensor transformation property. So I can write epsilon prime as A epsilon A transpose, where my A is a transformation matrix. So when I substitute all these, I get epsilon 1 1 prime as this equation. And we can see that epsilon 2 1 and epsilon 1 2 are the same. So I can just write this twice and this is gone. So this I'll call equation 1. Now in this equation 1, epsilon 1 1 prime is given to us. Epsilon 1 1 is given to us and the theta value is also known. If I substitute these with the value of theta as 60 degrees, that's pi by 3. So when we put in the values, we get an equation in epsilon 1 2 and epsilon 2 2 as the unknowns like this. So this I'll call A. Right. So now if I look at equation 1 here, I can also write epsilon 1 1 double prime, and this time my theta is equal to 120 degrees. That's a 2 pi by 3. So again, epsilon 1 1 double prime is given to us. That's a longitudinal strain. Epsilon 1 1 is given to us and theta is given to us. So when we substitute the values, we get another equation in epsilon 1 2 and epsilon 2 2 like this, and this we'll call B. So now we have to solve A and B. So I can simply add the two, which results in a 4 root 3 times epsilon 1 2, and that is equal to an 8. So from this, epsilon 1 2 is 8 by 4, which is 2 upon root 3, which is typically written as 2 by 3 times root 3. So this is my epsilon 1 2. And next is to find epsilon 2 2. So I can substitute this value in B. So thrice epsilon 2 2 becomes 4 plus 11, which is a 15. This implies epsilon 2 2 is 5. So we have successfully found out the values for epsilon 1 2 and epsilon 2 2. We had to find a gamma 1 2. Now gamma 1 2 is simply twice of epsilon 1 2. So that becomes a 4 upon root 3. Next is we have to find epsilon 2 2 prime. So if you look at the figure here, then epsilon 2 prime is at 90 degrees to x1 prime. So this is my x2 prime direction. So if I want to find the longitudinal strain in this direction, this is basically 90 plus 60, that's 150 degrees from x1. So all I need to do is I need to write epsilon 2 2 prime using the transformation with theta equal to 150 degrees. Epsilon 2 2 prime becomes like this. Epsilon 1 1 is known. Now epsilon 1 2 and epsilon 2 2 are also known, and theta is 150 degrees. So when we substitute all these, we get epsilon 2 2 prime as a minus 2. Now remember, there's a 10 to the minus 4 factor with all these. I'm not writing that for convenience. Now finally, it is asked that we have to verify that the first strain invariant is preserved by showing that this is true. Now while doing this multiplication here, I did not show you that epsilon 3 3 prime is equal to epsilon 3 3, but we'll need that for this part. So the first invariant of epsilon is given as this, and when I substitute the values, epsilon 1 1, which is a minus 3, epsilon 2 2 was found out to be 5, and epsilon 3 3 we will leave as it is because we do not know this. And the first invariant of epsilon prime is, now epsilon 1 1 prime was given to be 4, epsilon 2 2 prime we found out to be minus 2, and epsilon 3 3 prime is simply epsilon 3 3. So the first one becomes 5 minus 3, which is a 2, And the second one is 4 minus 2, which is also a 2, and there's an epsilon 3, 3 added to both. So we can see that the first invariant of epsilon is indeed equal to the first invariant of epsilon prime, so that completes the solution. So with this, we come to an end for this tutorial for week 8. I hope after solving these problems, you have a better understanding of the various quantities which are used to quantify deformations, and these quantities are the deformation gradient tensor, the displacement gradient tensor, the finite strain tensors Lagrangian and Eulerian, and the infinitesimal strain tensor epsilon. So thank you very much, and I will see you in the next week.